talking now? This is the 27th lecture, and we are going to complete a discussion on Laplace transform. We start with a question which was raised on an earlier occasion, last time. In fact, what we said is that if x of t is one-sided signal, that if x of t is 0 for t less than 0, if it is a one-sided signal, then we proved that Laplace of dx dt is equal to s times capital X of s minus x of 0 plus, right? We proved this. And then a question was raised, and I said I will take it up at the right moment. The question was raised, suppose x of t is ut, then Laplace of dx dt means Laplace of delta t should be equal to s times Laplace of x of s is 1 by s minus u of 0 plus is 1, and therefore it should be equal to 1 minus 1 equal to 0. Where is the fallacy? On the other hand, we know that Laplace of delta t is equal to 1 if we integrate directly. That is integral minus infinity to infinity or 0 to infinity, does not matter, delta tau e to the minus s tau d tau, this is equal to 1. Where is the fallacy? Why? How come this is 0 and the Laplace of delta t is equal to 1? The argument, the reason goes to the fallacy in the proof of this relationship. How we proved it was the following. We said that integral 0 plus to infinity, can you see this color on the monitor? 0 plus to infinity x of t e to the minus st dt, we said we will integrate this by parts. That is, what we said is first function x of t times integral of the second 0 plus to infinity minus integral of the differential of the first function, that is dx dt, then integral of the second e to the minus st by minus s times dt integrated from 0 plus to infinity. And you see the fallacy. When x of t is u of t, then dx dt is delta t if x of t is u of t, and integral delta t dt 0 plus to infinity goes to 0, and therefore this formula that Laplace of dx dt is equal to s times x of s minus x of 0 plus does not apply to a function like a delta function or a function like u of t, the unit step function, because its derivative at 0 plus is 0. It only exists at t equal to 0. This is a very special case, and one should take note of this. Now, to review what we had done so far, we will write down some Laplace transform pairs, and you will see how they can be remembered without consulting a book or a table. We will write the x of t here, and we are writing the bilateral Laplace transform and capital X of s here. First is, if it is a delta t, we have just seen that the Laplace is 1. If it is u of t, now the ROC should also be written along with the Laplace transform. This is all s, alright. If it is u of t, then the Laplace is 1 by s and the ROC is real part of s greater than 0. This is a right-sided ROC or a right half ROC. On the other hand, if the function is u of minus t, that is if the signal is a left-sided signal, the Laplace transform is the same 1 by s, but the ROC becomes a left half plane, that is real s less than 0. You must distinguish between the two. If the function is t to the n minus 1 divided by n minus 1 factorial u of t, then the Laplace transform is 1 by s to the n. 1 by s to the n and the ROC is real S greater than 0. On the other hand, if I put a negative sign, t to the n minus 1 factorial, and it is u of minus t, the Laplace transform is the same, 1 by s to the n, but the ROC is now the left half plane, the plane to the left of real part of s equal to 0. All right, we proceed like this. Then we have e to the minus alpha t u of t, and the the Laplace transform is s plus alpha real s. The time function will show what the ROC is. This is a right sided signal, and therefore the ROC must be the right half plane, plane to the right of real part of s equal to minus alpha, that is real s minus alpha. Is that correct? On the other hand, if I had minus e to the minus alpha t, note this negative sign. People often make mistakes here. If it is a left sided signal like this with a negative sign minus, the Laplace transform is the same, but the ROC becomes real s less than minus alpha, a left sided sequence. Then we take the most general case, that is t to the n minus 1 divided by n minus 1 factorial. Then we take e to the alpha t minus alpha t u of t, and as I said, this transform is most important transform because it is used in the inversion of Laplace transform by partial fraction expansion, and the Laplace transform is s plus alpha to the n. These transforms should be at the end of your names. You just have to scratch it to find out. You should not be required to consult a handbook. And the ROC is real s greater than minus alpha. And in a similar manner, if I attach a negative sign and instead of u of t I use a u of minus t, the Laplace transform remains the same, but the ROC changes to real s less than minus alpha. All right. Then we take, am I going too fast? A bit. All right. Have you been able to take this down? Then we take the delta function. Delta function, we have already said delta t is 1 all s. If I delay delta t by, let us say, tau, then the Laplace becomes e to the minus s tau, and this is the ROC does not change, it is still all s. The 2 or 3 transforms which you did not do in the class is cosine omega 0 t ut, and this the obtaining of this transform requires recognizing that cosine of omega 0 t is half of e to the j omega naught t plus half e to the minus j omega naught t, and that Laplace transform is a linear operation. You know the Laplace of e to the minus alpha t ut, so there is no reason why you cannot put alpha equal to j omega or minus j omega and obtain the transform, simplify, and the simplification would simply give you s divided by s squared plus omega naught squared. This is what it shall be. Now, what should be the ROC? ROC is this is a right sided signal, and therefore the ROC should be a right half plane to the right of the rightmost pole. Now, where are the poles? On the j omega axis, and therefore the ROC should be simply real s greater than 0. That is correct. Now, suppose I want the corresponding one for a left sided signal, that is I multiply by u of minus t and take minus cosine omega 0 t, then the Laplace transform remains the same, but the ROC changes to real s less than 0. I will not write this down. In a similar manner, if I take sine of omega 0 t u of t, then the Laplace transform becomes omega 0 divided by s squared plus omega naught squared, and the ROC is the same, real s greater than 0, because the ROC depends on the poles, not on the zeros. This function has a 0 at s equal to 0. This function does not. How many zeros does this have? 2. One at origin and the other at infinity. This function has 2 zeros, both of them at infinity. The zeros do not affect the ROC. It is only the poles, therefore the ROC remains the same. And finally, we generalize this by multiplying by e to the minus alpha t. If I multiply e to the minus alpha t cosine omega 0 t ut, this is some x of t, then the only change that occurs is s is replaced by s plus alpha, which we have done, and therefore this would be s plus alpha divided by s plus alpha whole squared plus omega squared. Now what happens to the ROC? The pole changes from plus minus j omega naught to minus alpha plus minus j omega naught, and therefore the real part of s should be greater than minus alpha. That is correct. And in an exactly similar manner, if I instead of cosine I take the sine function, sine of omega 0 t ut, then all that happens is omega 0 remains the same, s plus alpha whole squared plus omega naught squared, the ROC remains the same. If you know this table, then you can solve any problem in Laplace transform, however complicated the problem is. And this is one reason why I wanted to go through these transforms one by one. We next consider application of Laplace transform, and the major application, the motivation for learning Laplace transform is the analysis of linear time invariant systems, LTI system analysis by Laplace transform, LTI system analysis by LT. And the basic premise or the basic concept which is utilized is that if we have an LTI system, then e to the st is an eigenfunction. The response would be of the form h of s e to the st, where h of s is the integral of minus infinity to infinity ht e to the minus st dt. In terms of Laplace transform, now you see that capital H of s is nothing but the Laplace transform of the unit impulse response. In other words, if we know x of t, and then by convolution you know that if instead of e to the st the signal is a general signal x of t, then the output y of t should be x of t convolution h of t, and therefore the output transform y of s by convolution theorem should be simply capital X of s times h of s. That is, if you know h of s, if you know the Laplace transform of h of t, then you know the response to an arbitrary signal, and that is the major use of Laplace transform. We have to give a name now to h of s. In the case of Fourier transform, we argued that if the input is e to the j omega t, then the output is of the form h of j omega, which we, for simplicity we wrote as h of omega all the time. We did not write that j. But now when you go from Laplace to Fourier or from Fourier to Laplace, you have to include j omega now instead of h of omega. In any case, in the case of Fourier transform, we said that if s is j omega, that is the input is e to the j omega t, then the output is h of j omega e to the j omega t, and we gave a name of frequency response function to h of j omega. In this case, it is not just frequency, it is a complex frequency. It has a real part, s has a real part sigma and an imaginary part omega. So h of s, to be able to distinguish between frequency response function, which is the Fourier transform of the unit impulse function, in order to distinguish between that and the Laplace transform of h of t, h of s is given a new name. H of s is called a system function, or sometimes a transfer function. Transfer function. It should be recognized that if you put s equal to j omega, and if h of t is Fourier transformable, what is the condition for h of t to be Fourier transformable? In terms of Laplace transform, the ROC must include the j omega axis. In other words, if the ROC of H of S includes the j omega axis, then putting S equal to j omega shall give us the frequency response function. All right, this must be made clear that the Laplace transform may exist, the Fourier transform may not exist. It may be wise, or it may be quite appropriate to talk about H of S, but it may not be appropriate to talk about H of j omega, because H of j omega may or may not exist. All right, this must be distinguished. Now, obviously, you see H of S for rational systems, that is for lumped systems, H of S is of the form some constant multiplied by a polynomial divided by another polynomial Q of S. In case H of S is rational, obviously you see H of S is completely characterized by its zeros, that is the zeros of P of S, by its poles, which are the zeros of Q of S, and the multiplicative constant K. In other words, all that we need is a pole zero sketch in the complex S plane, and in addition we want just one spot value of H. For example, you could be given H of 0, or you could be given H of infinity, or H of j1, any value would do. Any value would then characterize at the zeros. Oh, at the poles you cannot define H of S, so it blows up. Yes, at the zeros H of S is 0, so it's already known.
So that's what I'm saying. So the value, in addition, the spot value should not be at the 0. Yes, it should be at some other point.
That is correct. A non-zero finite value. All right. Otherwise, we cannot find out H of S. So what is to be remembered is that the nature of H of S, that it is its variation with the variable S, is characterized by poles and zeros only. What K does is simply to lift the response or downgrade the response. That's about all. It's a scaling constant. So the nature or the response or the performance of the system is basically determined by zeros and poles. All right. Now, let's turn to something else. You know that the condition for stability of an LTI system, BIBO stability, which we have done quite early in this course, condition for stability is that the impulse response should be absolutely integrable. That is, mod of h of t dt, this should be less than infinity. You also know that this is a sufficient condition for the existence of Fourier transform. Isn't it right? If this is true, then the Fourier transform shall exist. What is Fourier transform after all? Minus infinity to infinity, h of t e to the minus j omega t dt. This must exist. All right, Fourier transform exists. So capital H of j omega exists. All right. Now I turn it the other way around. Suppose H of S is we are able to find out. H of S we are able to find out, and its region of convergence is known from the nature of H of t. Its region of convergence is known, and the region of convergence includes the j omega axis. What does it mean? If I go back in our argument, H of S region of convergence includes the j omega axis, and therefore the Fourier transform exists. If the Fourier transform exists, then h of t must be absolutely integrable. In other words, the system must be stable. So from the ROC of the Laplace transform of h of t, that is from the ROC of h of s, the system function or the transfer function as the name we have given, from the ROC we can also conclude whether the system is stable or unstable. All right. Is this clear? If h of s includes the ROC, the system includes the ROC of h of s, includes the j omega axis, the system must be stable. Otherwise, the system is unstable. We can also conclude from the ROC of h of s another characteristic of the system, that is whether it is causal or non-causal. Let us see. how this can be done. Well, suppose our h of t is right sided. Suppose h of t is right sided, that is h of t is 0 for t less than some value capital T. Then you know its ROC of h of s ROC shall be a right half plane. Is that correct? So, if h of t is right sided, the ROC is a right half plane. If h of t is causal, then what is the ROC? If h of t is causal, if it is causal, it must be right sided. Isn't that right? H of t causal means what? H of t is 0 for t less than 0. So, h of t causal shall mean ROC is RHP, some right half plane. And you notice that I have put two arrows, that is I can go either from here to here or from here to here. Is that correct? Is that assertion correct? No, it is not correct. It is not correct. The ROC is the RHP does not mean that h of t is causal, because all it means is that h of t is right sided. Now, right sided, the function could start from here. Instead of from t equal to 0, the function could start from, let us say, minus 1. Obviously then, if this is h of t, obviously h of t is not causal. Isn't that right? Causality of h, it is very easy to be mistaken, to be misled here. The reverse is not true. If the ROC is an RHP, you cannot immediately conclude that h of t is causal. In a similar manner, if the ROC is an LHP, left half plane, you cannot conclude that the system is non-causal. It may be causal, it may be non-causal. All right. It depends on whether the impulse response starts from t equal to 0 or not, because that is the concern with regard to causality or non-causality. All right.
So,
yes.
But if the ROC is some left half plane,
is some left half plane,
the signal HT is left sided.
Correct.
So does it also mean that HT, if the ROC is the entire, it goes from some particular value till the
infinity
to minus infinity?
Correct.
Then the signal will go on extending till. Does it mean this?
It means that, it only means that the signal is a left sided signal. It does not mean that it starts from t equal to 0.
Does it mean that the signal is bounded between some finite lower value?
No, no. Causality and non-causality have nothing to do with stability. These are two independent characteristics.
No, he is not asking stability in that magnitude sense, in the time sense.
Till some particular
Is it a sort of a gate or something?
A sort of a gate, it may extend right up to minus
That's what he
infinity.
is asking.
Yes, yes.
Then it's non-causal.
No, but it's possible it may be bounded.
If the ROC is left sided,
LHP, then it's non-causal.
then it may be non-causal.
It has to be non-causal.
Maybe it can be this sort of.
Alright, you sort this out yourself. You sort it out yourself. Let me leave some problems also. Actually, that question of ut and delta t, I was planning to give it in minor 2. But then since it was asked in the class, I thought we might as well explain that, but because that's it. Similarly, I'll leave some questions unanswered and you can take the hint. Let's take some examples. E to the minus t ut. Suppose this is h of t. I'll ask it in a different manner. I'll give you a sketch and then I'll ask you what kind of a system is this. I'll give you a sketch of poles and zeros and perhaps ROC, or I might ask what are the possibilities. Well, I'll be prepared. We'll do some problems in the tutorial class. Suppose my h of t is this, then from h of t itself you can conclude that it is a causal system, isn't that right? And is it stable? Yes, it is stable. From h of t itself you can conclude that, because h of t is absolutely integrable and it's 0 for t less than 0. Now, if you go to the Laplace domain, h of s equals to 1 by s plus 1 and the ROC is real s greater than minus 1, alright, real S greater than minus 1, this is minus 1 and this is my ROC. Now can you say whether it is stable and causal from this diagram?
It is stable.
It is stable because it includes the j omega axis. What about causality? How do you know?
So we'll have to find that.
From this diagram, we correct. So if you invert it, of course, you without inverting, given this only, can you say whether it is causal or non-causal? That's because there is only one pole. Well, if this is at minus alpha, then you know 1 by s plus alpha, 1 by s plus alpha will lead to e to the minus alpha t ut, and therefore you know that it is causal. But in general, it may not be possible. I will complicate the picture by taking an example. Now, let us say we take h of s, same function with e to the s, and the ROC is real s greater than minus 1. E to the s has only 0, so the ROC is the right of the rightmost pole. Now, is this stable? Is this causal? Let us see. Let us investigate. Stable, causal. Okay. Now, so we know that e to the minus t ut, the Laplace is 1 by s plus 1, real s greater than minus 1. Now, if I advance the signal by 1 second, then I get e to the minus t plus 1 ut plus 1, all right. This will be e to the s divided by s plus 1, real s greater than minus 1, and therefore the unit impulse response corresponding to this system is simply e to the minus t plus 1 ut plus 1. Obviously, it is stable because the ROC includes the j omega axis, real s greater than minus 1. But by looking at this function, you see h of t is not 0 for all t less than 0. Here h of t is 0 for t less than minus 1, not for t less than 0, and therefore the system is non-causal. It is non-causal but stable. Let us take another example and this will be fun. The next example, we have s minus 1 divided by s plus 1, s minus 2. ROC is not specified. This is the impulse response, this is the transform of an impulse response. Now, what are the possible ROCs? Let us take one by one. Sigma j omega, we have a 0 at plus 1, we have a pole at minus 1, and we have a pole at minus 2. Pardon me? Pole at plus 2. Pole at plus 2. Okay. Now, suppose I say that the ROC, one of the possibilities is that the ROC is to the right of this, right of the rightmost pole. Well, what kind of a system shall you call this? Is it causal? It is unstable, first of all, and all you can say, isn't the system causal? We don't know. Well, it's the h of t is right-sided, that you know. H of t is a right-sided signal. Whether that includes t equal to 0 or not, we don't know. If it is a right-sided signal and we transform and we take the Laplace inverse of this, well, I demand that it is causal, and I leave it to you to prove it. It follows from the picture, but I leave it to you to think about it. Let us take the other situation, h of s equal to s minus 1 divided by s plus 1, s minus 2. and we demand that the system be stable. That is, we know that the system is stable. The ROC, what is the ROC then? S equal to 1 is a 0, S equal to 2 is a pole, and S equal to minus 1 is a pole. Minus 1, 1 and 2. What shall be the ROC? System is stable, and therefore it must contain j omega axis, so it must be between this. Can you say whether the system is causal or anti-causal? Causal or non-causal? Let's put it that way. Is it causal or non-causal? If the ROC, now you have to think a little bit, if the ROC is a strip, obviously one of the poles calls for a left half plane ROC. Another pole calls for a right half plane ROC, and it is the intersection between the two, and therefore the system must be non-causal. All right, we can definitely say the system is non-causal.
Similarly, sir, we can say in the previous question that it is causal.
That's what I said. I demand that it is causal. Now it's up to you to prove it. Let's take the third situation, S minus 1, S plus 1, S minus 2. And once again I show 0 at plus 1, pole at plus 2, and pole at minus 1. Now, it is known that the system is neither causal nor stable. Then obviously the ROC will be this, left of the leftmost pole. Obviously it is a left-sided sequence, and you can show that it is not stable because it does not include the j omega axis. So unstable and non-causal. Unstable and non-causal. Okay, that's.
When it is a wire strip, it should imply it should be non-causal always.
Yeah, because it's a combination of a left-sided ROC and a right-sided ROC.
Can't it lie in the positive half altogether? Combination of left and right.
Then the ROC should be a single line, the j omega axis. If S equal to 0 is the dividing line, it's the only line of intersection, then the ROC is that, and obviously it is causal then. If it is a strip of finite width, then it cannot be causal, it must be non-causal. Okay. Now this situation of H of S, will apply if H of S is given along with its ROC, or the nature of the system is known, then you can find ROC. Is the point clear? We are given H of S and the ROC, then you can conclude about the stability and causality of the system. Of course, it is given that it is LTI, otherwise these do not hold good. All right, otherwise all of these comments fail. Okay. On the other hand, if the ROC is given and H of S is given, then you can conclude about the nature of the system, whether it's stable, unstable, causal, non-causal. But usual picture would be none of them are given. H of S has to be found out. What is given? What should be given about the characteristics of a system? Obviously, its description by a differential equation. No, poles and zeros come much later. The physical system, for example, an LCR circuit, all you can do is to write an equation in the time domain, and that would be a differential equation. So, system description, analog continuous time system description in practice, if you are let's say investigating the vibration of a stretched string, or the vibration of a pendulum, or the behavior of a given RLC circuit, or an active filter, all that you can do is to write a differential equation of the form AK dKyt dTk summation equals to summation Bk dKxt dTk. This will be the general form of the differential equation, and if the system is LTI, then you know that the coefficients, well, a constant coefficient differential equation, does it let me ask the question properly. Suppose I am given a constant coefficient differential equation. Does it necessarily imply that it describes a linear time invariant system? No, you should remember that. It is only under initial rest that this happens. Now suppose the system is not at initial rest. Can you still find out the response of the system? We'll come back, we'll come to this. But first, let me say, if the system is described by a differential equation like this, then since Laplace transform is a linear operation, we can Laplace transform each of these terms and we can find out capital Y of S divided by capital X of S if both are Laplace transformable. If not, then this description fails. We can find out the ratio of these two, and you know this ratio is the system function or the transfer function H of S, and we can find this out by inspection. Obviously, what we are taking is bilateral Laplace transform, that is two-sided function x of t or y of t. Then the question of initial conditions does not arise. Is this clear? We are saying y of t exists on both sides of t. X of t exists from both sides of t, that is from minus infinity to plus infinity. There are no initial conditions then. Agreed?
So what you need one?
Pardon me?
So we take the left hand side.
Yeah.
When k is 0, it's a0 into yt.
Correct?
So when you take the transform, if
Yes.
yt is right sided, then you'll have to subtract y0 plus.
We are not saying it is right sided, we are saying it's two sided. Suppose it is, then we will come back. Then we will have to specialize the.
So because yt is 0 for t less than 0, that's from initial rest.
We are not assuming initial rest now. We are saying it's a completely general equation where x of t is two sided, y of t is also two sided. Alright. If that is so, then we can find out h of s simply by taking transform of both sides, and obviously what you see is that it should be summation bk s to the k divided by ak s to the k. In other words, we can find out h of s as a rational function, that is a ratio of polynomial to another polynomial. This h of s is, however, useless unless the ROC is specified. Unless the ROC is specified, this h of s is useless. But nevertheless, if we know something more about the system, for example, we know initial rest, then we know the system is linear. Then we can also find out whether it's causal or non-causal from the ROC, if the ROC is given. But the first thing that you do is to find out the system function or the transfer function. Along with more information on this, and we shall work out quite a few examples of this, along with more information you can then come to a description of the system and find out whether the system is LTI, whether the system is causal, whether the system is stable or not. More about this a little later. But we shall quickly discuss something of system interconnections. We have done this again and again in connection with Fourier transform, discrete time signals and systems and so on. And we have said that if there are two systems, one following another, they are LTI systems with system functions h1 and h2, then the overall system function is h1s, h2s, which is simply the Laplace of the convolution of h1 of t with h2 of t. And therefore, if a complicated system can be looked upon as the series connection, or what is known as, didn't I introduce this term, cascade? Yes. If a system can be looked upon as a cascade of two or more systems, then the analysis becomes simplified, because you can find out the system function of each of these subsystems and then multiply them out. On the other hand, if we have a system which can be looked upon as parallel connection of two systems whose outputs add, then the overall system behaves as the sum of the two systems. That is, the system function is the sum of two functions. Obviously, the processing that occurs here, the output of H1 goes to the input of H2. So, it is a serial processing. On the other hand, here it is parallel processing. Okay. So, this is called a parallel interconnection. The third type of interconnection, which is new, at least for this course, you must have done it in Principles of Electronic Circuits, is the feedback interconnection. That is, we have a signal x of t, which is processed by a linear system whose system function is h1 of s, and then whatever the output is, let us say y of t, this is fed back. This is fed back through another linear time invariant system h2 of s, and the output of this is subtracted from the input. This is plus and this is minus. This is called a feedback system, and you will get plenty of feedback systems in practice, in control, in communications, in circuits, in active circuits, amplifiers, and so on and so forth. And you can show this also, I shall leave for you. You can show that h of s is given by h1 of s divided by 1 plus h1 of s h2 of s. This sign, if this sign is plus, then this sign becomes minus. If this is subtraction, then it becomes addition here. So, this is the third type of interconnection, and almost any practical system can be looked upon as a mixture of all the three kinds of connections, that is series, parallel and feedback. Finally, we come to a short discussion on the unilateral Laplace transform and its applications. We have so far discussed only bilateral. Only in the context of the initial value theorem and the final value theorem did we discuss signals which were strictly causal, that is x of t which was 0 for t less than 0. For such signals, obviously the Laplace transform definition starts from 0, and this 0 is to be meant as 0 plus. So, 0 plus to infinity x of t e to the minus st dt, and this is called the unilateral Laplace transform. Sometimes one uses a different symbol, but we shall use the same symbol. It should be clear in the context what we are talking of. All right. Now, the unilateral Laplace transform and the bilateral Laplace transform may be quite different. And to take an example, let us take this example, x of t equals to e to the, what about the ROC of such Laplace transforms, unilateral Laplace transform, ROC?
Right side.
Always a right side plane, okay, always, alright. And if xt equal to 0, t less than 0, and if x represents h, the impulse response, obviously the system is also causal, isn't it right? And that is where the major application of the unilateral Laplace transform is, that is LTI causal systems, LTI and causal systems are easily analyzed by unilateral Laplace transform rather than bilateral Laplace transform, all right. But one need not be too fussy about this. Even if you apply blindly bilateral Laplace transform, no harm is done, you will get the correct result. Only thing is that this is slightly simplified. Let us take this same example, e to the minus alpha t plus 1, no alpha, okay, e to the minus alpha t plus 1, u of t plus 1. Let us take this particular function. Then we know what its bilateral Laplace transform is, BLT. We know what it is, we have just done this. This will be e to the s divided by s plus alpha. We did it for alpha equal to 1, okay. Real s greater than minus alpha, all right. On the other hand, if we take the unilateral Laplace transform of the same function, xt equal to e to the minus alpha t plus 1 ut plus 1. If we take the unilateral Laplace transform ult, then x of s 0 plus to infinity e to the minus alpha t plus 1.
So what will be from minus 1 plus?
Yeah, that's a unilateral Laplace transform is defined with 0 plus as the lower limit. This is the definition. It doesn't start from t equal to minus. If it starts from t equal to minus 1, obviously then it's bilateral.
So we are given the condition for unilateral Laplace transform at x equal to 0 for t less than 0.
Right. If it is not so, then it is forced to be so. Alright. So the definition is this. The heart of the definition is that lower limit is 0 plus. If it is not so, then it is forced to be so. For example, in this case, it is not so, but it is forced to be so. In other words, what we are doing is e to the minus st dt. And obviously, this would be e to the minus alpha divided by s plus alpha. Alright, this is not e to the s. The bilateral transform was e to the s. The ROC is the same, real part is greater than minus alpha, but the two are different. The other difference that arises is in the Laplace transform of dx dt. As we have already shown, it is s x of s minus x of 0 plus. Alright. We have already shown this, we have already proved this. On the other hand, if it was bilateral, then it is simply s times x of s. Alright. For unilateral, x of 0 plus is to be included. Now, if I take Laplace of d2x dt2, then obviously I can utilize the same formula by taking dx dt as y. This is simply dy dt, and therefore what we get is s squared x of s minus s x of 0 plus minus x prime of 0 plus. That is the first differential coefficient. And in a similar manner, if we go ahead like this, Laplace of dnx dtn, where should it start with? S to the n xs minus s to the n minus 1 x of 0 plus, and so on. Where shall it end? X of n minus 1 0 plus. This is the difference. One might ask now, why should we go into this complication? Why should we consider unilateral Laplace transforms at all? Because life is very simple if we simply keep powers of s. S xs, s squared xs, which will hold if it is bilateral Laplace transform. We don't care what x of 0 is. The reason for bringing in this is to solve linear time invariant systems. You know, initial rest is a condition, or initial conditions, forget about LTI systems, solution of differential equations with given initial conditions. This is done most comfortably by using unilateral Laplace transform. And we shall just demonstrate with one example how this is applied to solution of difference equation with given initial conditions. And the equation that we take is y double prime plus 3y prime plus twice y equal to twice u of t. Alright. Obviously, you require two initial conditions to solve this, and these initial conditions are y of 0 equal to 3, y prime of 0 plus equal to minus 5. Can this be, first condition, can this describe a linear time invariant system? Can this describe a linear time invariant system? Yes, because the initial conditions are at 0 plus, not at 0 minus. It can be at rest. Alright? And if it's a second order differential equation, then how many conditions do you require for initial rest? 2. That is the function and its first derivative. And therefore, this could describe a linear time invariant systems. But you see, the solution is very simple. What we get is, if we take the Laplace transform of both sides, then you get s squared capital Y minus s y0 plus, which is 3, minus y prime 0 plus, that is minus 5, alright. This is the differential, this is the Laplace of y double prime, plus 3 s y capital Y minus y0 plus, which is 3, plus 2 capital Y equal to 2 divided by s. As far as ut is concerned, bilateral or unilateral, does it matter? No, it doesn't matter. Now from here you can find out capital Y, and the capital Y that you get after simplification is 2 divided by s, s plus 1, s plus 2, and you can now find out, I am going to ask you a question, you can now find out the inverse transform by expanding in partial fraction and inverting term by term. That is the question. How do we solve that question? What is the ROC?
If we take it on the right side, unilateral transform, then
yes,
it will be right sided thing.
That's correct.
The right of the rightmost pole.
Yeah.
So it should be to the right of the rightmost pole. Yes, okay. So the ROC here should be real part of s greater than 0. That is right. This, who forces this?
Equation UT.
That is correct, because we are taking unilateral Laplace transform, alright, and the system is also, the equation also says that it is at initial rest. So t equal to 0 is the starting point, and all we are talking of at t equal to 0 plus, and therefore ROC is real part of s greater than 0, and all that you get from here is multiplied by ut. Small y of t shall be multiplied by u of t. And with that we come to the end of Laplace transforms. We shall work out a very large number of examples in the tutorial class, and therefore we have distributed the tutorial class to 2 sessions. We will work out a large number of examples, and in the next lecture class we start Z transforms.